More than 7,500 active satellites are currently in orbit. Together, they provide GPS navigation for every smartphone on Earth, weather forecasting that saves thousands of lives annually, internet access for regions that have no ground infrastructure, and the military communication backbones of every major power. Every launch adds capability. Every constellation deployed adds services that modern civilization has built dependencies on and cannot easily replace with ground-based alternatives. The momentum of the space economy is real, the services are valuable, and the launches are accelerating. More payload mass reached orbit in the last 5 years than in the previous 5 decades combined. Every satellite we launch makes the next one more dangerous, and past a certain threshold, none will be able to launch at all. That sentence is not a claim about launch technology or rocket engineering. It is a description of what happens when a finite shared resource accumulates waste faster than it disperses, and the waste is capable of generating more waste on contact. The orbital shells around Earth are finite, defined altitude bands where objects maintain stable orbit without constant propulsion. The debris in them stays, sometimes for decades, sometimes for centuries, depending on altitude. And above a certain fragment density, a single collision between two objects produces enough new fragments to trigger further collisions, which produce more fragments, until the shell becomes permanently impassable by any object, operational or not. In 1978, NASA scientist Donald Kessler published a paper formally describing this cascade scenario. The paper calculated that above a certain debris density threshold in low Earth orbit, the collision rate between existing debris objects would be self-sustaining, meaning new fragments would be generated by collisions faster than atmospheric drag removed them from orbit. The process, once initiated, would not require any additional launches to continue. It would run on the existing debris population. The orbital shell would fill with fragments over decades until it was functionally impassable for any spacecraft attempting to transit it. Kessler published that paper 48 years ago. In the decades since, the tracked debris population has grown from a few hundred objects to more than 27,000. The estimated population of objects between 1 and 10 centimeters, too small for current radar systems to catalog reliably, too large to survive an impact with an operational satellite, is approximately 500,000. The number of objects smaller than 1 centimeter, large enough to penetrate a spacesuit or damage a solar panel, is estimated in the tens of millions. None of these numbers are decreasing. Every launch deposits hardware into the orbital environment. Every collision between existing debris objects creates new fragments. The population grows because the inputs exceed the natural removal rate, which for objects above 600 kilometers altitude is measured in decades to centuries. The warning was published. The debris count was tracked. The governance response that would have changed the trajectory was not built. Objects in low Earth orbit travel at approximately 7.8 kilometers per second. That number requires a concrete translation to mean anything. A rifle bullet travels at roughly 1 kilometer per second. A fragment the size of a marble moving at orbital velocity carries the kinetic energy of a hand grenade detonating at contact range. A paint chip at orbital velocity carries enough energy to pit a viewport or compromise a pressure vessel wall. The International Space Station has documented paint chip impacts in its windows. The windows are designed to absorb them. The orbital velocity is the same for the fragments that are too small to track and too large to be harmless. February 10, 2009. The Iridium-33 communications satellite and the defunct Russian Cosmos 2251 military satellite collided at 11.7 kilometers per second over Siberia. Neither satellite had maneuvering capability at the time of impact. Neither was in a significantly degraded orbit. They occupied the same orbital shell at the same altitude on intersecting paths, and the combined closing speed was higher than any rifle round ever fired. The collision produced more than 2,000 tracked debris fragments. The actual number of fragments, including all objects below radar tracking threshold, is estimated in the tens of thousands. Each fragment is now on an independent orbit. Each represents a future collision probability with every other object in the same altitude band. The cascade Kessler described in 1978 does not begin with one catastrophic event. It begins with events exactly like the iridium-cosmos collision, repeated with increasing frequency as fragment density rises and the orbital environment becomes less forgiving of every additional object placed in it. Below the cascade threshold, the debris problem is serious but theoretically manageable. Removal systems that intercept and deorbit high-risk objects can reduce collision probability faster than the natural accumulation rate adds to it. The math of cleanup works in the direction of improvement. Investments produce measurable risk reduction. The problem responds to intervention. Above the cascade threshold, the math inverts, and it does not invert gradually. A single collision between two significant objects, a defunct rocket body and an end-of-life satellite, for example, produces thousands of new fragments distributed across an orbital band. Those fragments individually intersect active satellite orbits, active debris objects, and each other. The collisions those intersections produce generate additional fragment populations. A cleanup system that can deorbit 10 objects per year is operating in an environment where a single cascade event has added thousands of new objects in minutes. The removal rate cannot exceed the cascade production rate. The debris problem becomes permanently unfixable, not because the removal technology failed, but because the threshold was crossed before the removal system was scaled to match it. The threshold itself is not a cliff with a clear edge. It is a statistical property of fragment density that changes with orbital altitude, object mass distribution, and the specific geometry of the populated shells. Current models suggest that several critical orbital bands are approaching threshold conditions. The models disagree on the precise margin, which is exactly the kind of ambiguous warning that governance systems are structurally worst at responding to. Not a confirmed crisis, not a safely distant projection, but a probability distribution with a catastrophic tail that is moving towards certainty on a timeline shorter than the political response cycle. The failure chain that emerges from cascade threshold does not require a dramatic triggering event. It requires only the continuation of current launch rates and current deorbit compliance. A fragment density event in the 550 to 800 kilometer altitude band, the most congested range, home to GPS-adjacent satellites, Earth observation constellations, and the majority of active broadband megaconstellation hardware, begin producing secondary collision events at a rate that exceeds natural orbital decay. Satellite operators in the affected band begin losing vehicles to fragment impacts. GPS accuracy degrades as constellation geometry becomes incomplete. Weather forecasting satellite coverage develops gaps. The broadband constellations that global emergency communication depends on begin losing nodes faster than operators can replace them. The economic infrastructure loss triggers a national response. Nations that have lost critical satellite coverage prioritize replacing their own infrastructure over debris mitigation coordination. Each replacement launch deposits new hardware into the band already approaching cascade saturation. The political pressure to maintain national capability overrides the collective interest in reducing orbital congestion. Individual operator decisions, each nationally rational, collectively accelerate the fragment production rate at the precise moment when deceleration is most needed. Adjacent orbital shells begin receiving fragment populations from the primary event. Each fragment that migrates to a new altitude band raises the collision probability for the objects already resident there. The cascade does not stay contained in the initial shell. It propagates outward through the altitude spectrum, progressively foreclosing crewed spaceflight launch corridors, then higher altitude communication and GPS bands, then eventually the geosynchronous orbital shell, where weather and communication satellites with 15 to 30-year operational lifespans have been accumulating since the 1960s. The process does not announce itself. There is no moment at which an alarm sounds and the cascade is confirmed. There is only the tracking catalog updating every day, the number climbing, and the collision probability estimates quietly crossing thresholds that were previously described as the boundary of acceptable risk. The proposed engineering solution is active debris removal, robotic capture vehicles that intercept defunct satellites and rocket bodies and deorbit them. The concept is technically demonstrated. ESA's Clear Space 1 mission represents the first funded operational attempt. The technology works in principle. The economics break in practice, and the math breaks above cascade threshold. Each removal mission must cost less than the collision risk reduction it provides per object to be viable at scale. For the 50 largest objects in critical orbital bands, defunct rocket bodies, spent upper stages, dead satellites, the risk reduction per removal is significant enough that the economic case can be made. Removing those 50 objects would reduce cascade probability meaningfully in the most congested shells. This is the removal program that debris physicists recommend as first priority. The 500,000 untracked objects between 1 and 10 centimeters cannot be addressed by the same program. They cannot be individually located, they cannot be swept because no sweeping architecture at any reasonable scale removes fragments faster than orbital dynamics redistribute them. The cleanup program and the cascade risk exist in different size regimes, and the size regime that matters most, too small to track, too large to be harmless, is precisely the range that removal programs cannot reach. The governance solution: binding international deorbit requirements, orbital traffic management, launch licensing tied to orbital carrying capacity, addresses the problem before cascade threshold and has no mechanism to address it after. The 25-year deorbit standard, currently followed informally by most major operators, was chosen for operational convenience, not debris physics. Debris physicists recommend 5 years. The difference between those two numbers, applied to the thousands of satellites currently in orbit and the tens of thousands planned for the next decade, is a fragment population delta that determines whether the cascade threshold is crossed before binding standards exist. The Kessler Syndrome is not a technology problem. It is a commons problem, a finite shared resource being consumed by individually rational actors whose combined behavior makes the resource permanently unavailable to everyone, including themselves. Every previous human commons collapse followed the same pattern: fisheries, groundwater, atmospheric carbon capacity. The threshold was knowable before it was crossed. The crossing was incremental rather than dramatic. The political response arrived after the point where it could have been effective. Orbital space is the first commons where the collapse is also physically irreversible on human timescales. There is no reforestation program for orbital shells. There is no equivalent of carbon sequestration for fragment populations above cascade threshold. The process, once running, runs on its own energy. The generation currently deploying the most satellites in history, building the most ambitious constellations, and planning the most launches of any period in spaceflight history is doing so in an orbital environment whose debris population has grown every year since 1957 without a binding international governance framework to manage it. The services those satellites provide are real. The economic value is real. The fragment population those satellites join at end of life is also real, and it accumulates in a system that has no self-cleaning mechanism and no enforcement architecture to compel the behavior that would prevent cascade. Artemis will attempt to return humans to the moon through the same low Earth orbital bands that mega-constellation deployment is filling. The launch corridors crewed vehicles use are not separate from the orbital shells where debris accumulates. They pass through them. Every crewed mission transits the debris environment at orbital velocity. The risk that environment represents increases with every object added and does not decrease with any deorbit compliance rate below 100%. The door to space is not locked yet. The people locking it are not acting irrationally. They are launching satellites that provide valuable services, following the standards that currently apply, and making decisions that are individually correct. The lock is being turned by the accumulated total of those decisions in a system with no mechanism to stop it before the threshold is crossed and no mechanism to reverse it after.